All right, so now we're going to use a vector math to work with relative velocity, which you've done it also in grade 11. I have an example here. An airplane flies due north at 235 kilometers per hour relative to the air. There is a wind blowing at 65 kilometers per hour to the northeast relative to the ground. What are the plane's speed and direction relative to the ground? So before we work with this problem, let's work quickly through some theory. But we have an equation that is, if I have pretty much, let's put it this way, we have a frame of reference. For example, say this is some sort of a medium A, and a medium A, whatever that is, air, water, conveyor belt, treadmill, it's moving in a certain way. And then we have an object, which is right here, and this object is moved with some velocity of the object with respect to the medium, right? However, the medium, so which means how we're measuring this velocity of the object, we're measuring, so we have a guy here, and he's observing it, he's on this medium, that's when he measures, right? However, our medium is another larger medium frame of reference. So this is observer 1, and that's what he observes. Now we have medium B here. Now the whole medium A is moving, let's say, like this, like that. Right, so this is the velocity of medium A with respect to medium B. So now we have another observer here. Let's call this observer 2. And what he sees is a whole medium A moving through medium B. For example, the ground and the conveyor belt. And this guy is in a conveyor belt, and this object, a mouse, is in a conveyor belt moving. So what this observer will see is the object actually moving with a velocity. Sorry, this is a velocity of the object with respect to medium B. Think of a river, wind, air, and whatnot. All right. So in general, so this is what observer 2 observed, and this is what observer 1 observes. So in general, relative velocity is the velocity of the object with respect to a second medium is the vector sum of the velocity of the object with respect to the medium where it is moving plus the velocity of the first medium with respect to the second medium. All right. So if we have, for example, air and ground, then we have the velocity of the object with respect to the ground is equal to the velocity of the object with respect to the air plus velocity of the air with respect to the ground. Air, for example, is the wind, right? Or if we have water and ground, we have the velocity of the object with respect to the ground is equal to the velocity of the object with respect to the water plus the velocity of the water with respect to the ground. Think of a river, the speed of the stream, and whatnot. And we have many options. So whatever the velocity of a car with respect to a planet, and the velocity of a planet with respect to another planet, and then you keep on adding. So that's the idea of relative motion. And there is no such a thing as absolute motion, and there is a limit of this, as you know, the speed of light, but we won't go there. So now let's go back to our problem, right? So what is given to us, let's go back to it, is the airplane speed with respect to the air. So the velocity of the airplane, the object with respect to the air, is 235 kilometers per hour and is due just north. And then the wind speed or the velocity of the air with respect to the ground is, I believe, is 65 kilometers per hour. And it says it's northeast, so which means north 45 degrees east. And we're looking for what is required from us to find the velocity of the airplane with respect to the ground. So which means we're looking for the speed, or in other words, the magnitude, and some direction with respect to the ground. All right. So many ways to solve this. We can do as always a component method. Let's just draw it to see what it looks like. So the airplane is moving pretty much north with respect to the air, so this is the velocity of the airplane with respect to the air. However, there is a wind going at 45 degrees with east. So this is the velocity of the air with respect to the ground. And what we want to find is this vector here, which is the velocity of the airplane with respect to the ground. All right. So we're looking for some angle and for magnitude. So you can use sine and cosine law, the triangle method, but we're going to use a component just so that we get a hang of it. So we have VOA, VAG, and VOG. All right. So we have the X and Y component. So the velocity of the object with respect to the air, X component is 0 kilometers per hour because it has no X component, it's just traveling north. And the Y component is positive because it's north and it's 235 kilometers per hour. And the VAG, the air, is northeast, so they're both positive. So it's 65 sine 45, which is roughly 45 kilometers per hour. I'm not worried about the significant digits too much now. It's just learning how to solve these problems. The same with the Y component, they're the same, and we add them up. So we have the X component of VOG, or the velocity of the object with respect to the ground, is 45 kilometers per hour, and the Y component is 280 kilometers per hour. So now we're able to find the magnitude or the ground speed of the airplane, which is square root of 45 squared plus 280 squared. So VOG is approximately 283 kilometers per hour. And the angle that the airplane is going to make from the ground point of view is inverse tan of 280 or VOGY over 45 or VOGX, and the angle is approximately 80 degrees. Could be more, could be less, but again, it's just to make a point. So now we can report, therefore, the velocity of the airplane with respect to the ground is approximately 283 kilometers per hour. It has a direction east 80 degrees north. All right, so that's how we work with relative velocities in 2D. In 1D, it's even easier because you don't have to deal with components. And again, there's a lot of practice on the textbook.